In this video, we're going to look at a couple of ways that we can combine some matrices together and then take the determinant and see what the result is. So one of them we've talked about already in class, but not on the video yet here. If I take a square matrix A and multiply it by a constant k, a real number k, that's going to multiply every entry in A by k. Take the determinant of that, what do we get? Well, we already know that if you multiply one row by k, you multiply the determinant by k. Well, this is going to multiply every row by k. So you're multiplying by k n times, and hence the determinant of k times a is k to the n times the determinant of a. There's that extra k in every single row. So that was simple enough. Now I want to look at adding two things together. And we've seen already that if you add two matrices together and take the determinant, that it's not equal to the sum of the determinants. But there is something that we can say. It says this: if A, B, and C are matrices that differ only in one row, let's say the rth row, and the entries in the rth row of C are the sum of the corresponding entries in the rth row of A and B, then it is the case that the determinant of C is the determinant of A plus the determinant of B. The proof maybe will explain what we're actually talking about here. So I've got three matrices, A, B, and C. Well, here's A. B is actually equal to A everywhere except for one row. For the sake of simplicity here, I'm just in the first row they differ. So the first row of B is different than the first row of A, but every other row is the same. So I'm using the same letters here as I used over here. Okay? Likewise, all of these rows of C are the same as they were for B and A, only the first row is different. But the first row, the entry in the first column here, is the sum of the entries in the first row, first column of A and B. And then in the second column, first row, second column, first row, second column, add them up. Right? So the entries in the first row of C are the sum of the corresponding entries in the first rows of A and B. Okay? And we could do this on any row, but I'm just choosing to do it in the first row. So then I say, well, just look at the determinant of C here. I'm going to do expansion over the first row, or the rth row if I wasn't in the first row. So I have this position times the cofactor, what's left, plus this position times the cofactor. Notice that the cofactors for each entry in the first row, the cofactor doesn't use the first row. And so the cofactors for C are the same as the cofactors for B or the cofactors for A, as long as you're looking at cofactors corresponding to entries in the first row. So when I look at the determinant for C, it looks like this. Then I can distribute in, and I've got A11 times C11 and A12 times C12 and so on. Likewise, there's going to be a B11 times C11 and B12 times C12 and so on. I put all those here. This is just the determinant of the matrix A up above, and this is the determinant of the matrix B. Okay. So we have the determinant of C is the sum of the determinants of A and B. Okay. Only in one row did C equal A plus B. In all the other rows, A, B, and C were identical, right? And then you get this property. This works on any one of the rows, or actually any one of the columns. There is a notion that we run into in later courses in linear algebra where you look at functions of several variables. So you look at, oops, what am I doing here? So I look at something like f of, a bunch of variables, x, y, z, whatever. And there's a question of whether they're linear functions, and some of them are not necessarily linear functions, but they're linear in each position. If you look just at the first position, you might find that f of a plus b y z is f of a y z plus f of b y z. That is, you keep the most of the variables the same here, here, and here, but you can add them up in just one location. And if that's true for any one of the variable slots here, then this would be what's called a three-linear form or something. There's the determinant is what's called an n-linear form because there's n rows, each one of them having this property. Okay. Something you'll get to in a more advanced linear algebra course, but it's something that is coming up, and this is sort of the first notion that you see of, first idea that you see of that notion.